Hey guys, welcome to the third video in the series of videos that I've been posting. Right, so in this video, we're going to talk about how you can actually get drag from conservation of momentum. Right, in the first two videos, we talked about lift, we talked about thrust, and then second, we talked about lift. And in this video, we're going to talk about drag. Now, in this in this drag component or drag from conservation of mass and momentum, part of the work will be your homework. Okay, but don't worry, I'm going to walk you through the different steps that you need to do the homework as well. Okay, now let's just intuitively understand what we are talking about here. I guess you guys know in the last two videos, I hope you guys are familiar with conservation of mass and momentum. Okay, now let's just consider you have a velocity coming in with a certain speed, like u infinity. And let's, for example, it's a classical, let's just hope that let's just place a classical cylinder um, in the test section or in the flow. Now you may you may think that, hey, here's a velocity meeting the cylinder, right? But since air has mass and is traveling at a certain velocity, let's just consider that the air that is meeting the cylinder has some momentum m1, which is basically mass times velocity, right? Just as say m1. Okay. Now, as you guys know, the behind the cylinder there will be shedding, right? There will be wake, and then there will be shedding. Now, let's think about what happens to the velocity behind it, right? So I'm going to put a series of arrows here, right? To closer to the center line of the cylinder, it is reasonable to expect that the velocity will be lower, right? And as you go to the free stream, you expect the velocity to increase, right? And then that happens on both sides, right? So towards the center, you get a lower velocity because you get huge wake here, right? And as you go more and more towards the free stream, you will match the free stream that you started with, right? So if we join this, the head of these arrows, you'll get a distribution something like this, right? Now, let's just think about it. This is the momentum that the air has when before it meets the cylinder. And this is the momentum that the air has before and after it passes through the cylinder, right? So just consider here's box. Okay, that's the momentum m1, and this is the momentum m2. Now, when you compare these two momentums, what do you think happened to the momentum of air that passes through the cylinder? Will it decrease? No, did it decrease or did it increase? I mean, you can see clearly that the momentum has actually decreased, right? Because if there is no momentum loss, all the arrows will have the same length, just like right here, right? You have the exact same copy behind the cylinder, but guess what? Because of the wake, your momentum is actually lost, right? And so that means your, M2 will be less than M1, right? Now think about this. What did Newton say? Newton said, hey, wait a minute. Anytime there's a change in momentum, there will be a force accompanied with it, right? So guess what that force is? That force is nothing but drag, right? It's the drag of the object which is causing the change in the momentum in the fluid. Or you can think of it the other way. The change in momentum of the fluid, um, because of the object, right? And the resultant force that the object experiences because of that is the drag force. Right. I hope you guys understand what I'm trying to say here, right? So again, there is a change in momentum, and that change in momentum is brought by this an object or this cylinder being in the flow, and the force experienced by that cylinder because of the change in momentum is the drag force. Okay, so that means if you want to minimize the drag force, just make sure there's a momentum loss is minimal in the wake, right? If you can do that, then you can make sure that the drag is reduced, right? So this is basic understanding. This is where the drag comes from. Okay, this is the reason for the pressure drag at least. Okay, now that's what you'll be working on in your homework. Okay, so the first thing that you'll be doing in homework is a theoretical, you're approaching the drag from a theoretical perspective, right? Remember the velocity profile that we talked about? This actually resembles a Gaussian profile, and that's what I given right here, right? It's right there. Okay, so just for our sake, we can consider that that velocity profile is given by this analytical expression. Again, it's a Gaussian profile, right? You have U infinity marks the free stream velocity, right? And by y, so you get your coordinate system, x and y, right? We assume that there's no change in velocity with respect to x-axis. We only consider the change in velocity with respect to the y-axis. Okay, what you're required to do here is that um, you're required to find what would be the drag coefficient acting on this airfoil if the wake profile is given by this expression. Okay, and you can get this by using equations of fluid motion, right? So right now we describe this intuitively, right? Now you have to derive an expression. So you have to come up with an expression like what? D equals something, right? Using conservation of mass and momentum, which allows you to, well, this should be a function of u infinity, right? So, or not infinity, but yeah, the velocity profile, because you know the momentum coming in and this is the momentum going out. The difference between those will basically give you drag, right? So, but I would encourage you guys to do to use MATLAB to actually solve this question. Okay. Now let's moving forward. You have to make some assumptions to solve this question. So make sure to assume steady, inviscid, no body force. For the moment, let's just assume no change in area, but that won't be really true because when the wake expands in order to conserve, well, in order to conserve mass, when the flow goes around the fluid, it has to expand. Okay, otherwise the mass won't be conserved. But assuming you place this in the test section, I'm trying to kind of give you guys a feel for how you can take this idea, this equation, and actually use it in experimental bridging. Okay, and for all intents and purposes, let's just make sure that it's a constant pressure on all sides, even though that's not true. Okay, the reason why we're assuming here is because we are assuming the pressure on this side equals to the pressure on this side, even though that's not really true. But the reason why we're enforcing this is because we want to make sure that the change in momentum is purely due to the drag force on the object, okay, and not due to the pressure variation between the side one and side two. Remember that even if there is a pressure variation, that will change the momentum, right? But to make our lives easier, let's assume that the pressure P1 equals pressure P2 on both sides, so that the change in momentum is only caused by the drag force of the object. Okay, that makes sense. Now, well, you may think that how I'm gonna derive an expression for this. So I put an expression here, but I also again, just to help you, I I hope, and realistically, I want you guys to derive the expression, but I understand it can be hard. So I actually derive some of the steps for you, and then I got you the final equation right there. But I'm not going to go through that in the video right now, but I want you guys to just go through the steps and make sure you at least understand what it is and where this equation came from and how it's being applied to this control volume. And don't just take the final equation and run with it. Okay. Now from this equation, all you have to do, look at that. You got u of y, right? U of y is basically this expression. And u infinity, you don't have to assume any values or anything. Just keep u infinity as it is. But this u infinity as it is. Okay. Now you have the drag force, which is exactly what you want. And from the drag force, you can actually determine coefficient of drag, right? So all you have to do is substitute this into the equation and then you integrate. And I recommend you guys using MATLAB to perform this integration, okay? Because I want you guys to learn how to use MATLAB to integrate and differentiate and all that, okay? So that is question one, okay? Now we're gonna switch to question two, which basically the same thing, right? It's you're gonna use the same equation, but except instead of an analytical expression like u of y, you will be given an actual data, okay, actual experimental data, which changes where you kind of have the variation in velocity in the wake of a wing. Okay, so the second question allows, ask you to determine drag coefficient for a very interesting case that we looked at a couple of years ago. Okay, now I'm going to explain what it is that you see here. Okay, now a couple of years ago we did research on a on an unconventional wing case called slotted wing. So what the idea behind here is that to allow the air to actually pass through the slot on the wings. The reason why we looked at this case is because, well, as you know, at the wingtip, you have the formation of the wingtip vortex, right? That is the wingtip vortex forming right there. And the idea behind doing this is that, if you look at what the wingtip vortex is doing, it takes the momentum of the air coming in, right? And then it changes that momentum into a different direction, which actually causes drag, right? Because whenever there's change in momentum, there's this drag, right? So the idea behind including slots is that it will affect the vortex actually, coming in. Okay, that's the idea behind the slotted wing. Now, in order to understand how the wake is different between an actual airfoil and a slotted airfoil, we did what is called particle image velocimetry, and we actually looked at the wake behind a slot. Okay, so we made sure to cover one end so that the wingtip vortex is not forming. But basically, this is what you get: like 2, 4, 6, and 8. These contours. Oh, look at that! I included a contour scale at this in this slide. What you see here are the velocity contours behind the airfoil, and there's a slot right there, and then the air goes through the slot, and this is the wake it leaves behind. Okay, and as you can see, as you change the angle of attack, the blue that keeps increasing a lot, which means that the velocity is actually reducing when compared to the free stream, right? That's why I normalized that velocity with respect to the free stream coming in. So with this ratio equal to 1, then the velocity in the wake is the same as the free stream, which actually happens in all these regions right here, right? In all these regions, it's the same. But once in the wake, the velocity goes down when compared to the free stream, right? So this is the data that you'll be getting. Okay, I'm not going to give you the actual contour. I simplified it even further by actually giving you a velocity profile. So I took a profile in here. So that's what you actually see right there. Okay, so the red lines represent behind an actual trailing edge of the airfoil, and the blue lines represent behind the slot of the airfoil. Okay, so again, this is the momentum deficit, right? From the momentum deficit, right, you can include this data. This is basically your U of Y, right? Exactly, just use the same procedure you did in the first homework, but in this case, when you integrate, you won't be integrating analytically, but you'll be integrating numerically. Like, hope that makes sense, right? So here you have u of y as a function of, as an equation, but in the second question, your u of y is basically that, right? It's basically this profile right here. Okay. Now these are non-dimensional, u x by u infinity and z by L naught. Your L naught here is basically the wake half width. So that just means that how my wake is actually growing, right? What's the thickness of my wake is, okay? So all you have to do to make this dimensional, but look at this equation, right? Everything is dimensional here, right? There's no terms which are non-dimensional. So all you can do is, you have L naught, right? So for 2-degree case for baseline, just multiply the profile by L naught by this number. You will actually get the Z, which is the profile in terms of dimensional quantities, right? So that's sort of, this is basically the velocity profile, and you integrate into this equation using trapezoidal command, right? There is a way that you can integrate in MATLAB, do numerical integration by a command called traps, right? So trapezoidal command allows you to integrate, right? So let me pull up the actual, um, keep this at the actual data set, okay? Okay, so hope you still can see here, right? This is the data that you'll be getting, okay? Um, so you have y by L naught normalized wake half width for baseline wing, right? And you have for the slotted wing. So what you can do is, and I'm just gonna, when I upload this spreadsheet, I'll make sure to plot everything for you, okay? So for 2 degrees, I'm gonna plot my x, I'm gonna plot my u infinity. So that's my baseline 2 degree, right? Now look, let's look at the data set right there, right? There's a Gaussian shape, but it's inverted, right? And what I'm gonna do, what I'm gonna do is just switch it so that you can see clearly. There you go, right? And what you notice here, you have this Gaussian shape, right? Now that's my u by u infinity, okay? Now let's look at the equation right here, right? The u by u infinity, I have to, that's that profile that we saw before, and this is my u infinity minus u infinity, okay? So what you can do is, so if this is your u infinity, I'm going to take this velocity, right? So, well, one thing that you can do is let's just consider u infinity as 1. Okay, let's just consider unity as 1. So 1 minus that, because what I'm doing here is I'm actually programming this term, right? That's my 1 minus u infinity, right? So, and then I'm plotting, this is, I'm going to say u infinity minus u of y, okay? That's the column here. This is for 2 degrees, okay? Now all I have to do is multiply it with u infinity again. So I'm going to create another column, take this and multiply that with this column again, right? Because that's my u by infinity, right? Now I have everything in here. I just have to integrate this, right? That's all I have to do to get the drag, right? And then we'll multiply by density, of course, but yeah, but you get the idea, right? I mean, all you have to know here is that how you're going to integrate this to actually get a number, right? So in MATLAB or even in Excel, there is a way you can numerically integrate, okay? So if you integrate this, you'll just get one final number, and that will be your drag value, okay? So I hope that makes sense, and hope that'll allow you to, to continue with this homework, okay? Again, at any point you have any questions, feel free to ask. All right. I'll see you guys. Bye.